Hello and welcome to the Cuyamaga Institute, our Q&A Conversation for Exploration series. I'm Paul Robert, the Executive Director and President of the Institute, and along with my wife, Laura Lee, the Director of Research, Education and Outreach, and of course on behalf of our Board of Directors, advisors, volunteers, supporting members, we want to thank you for joining us today. The Cuyamaga Institute is an independent, nonprofit educational research organization committed to researching consciousness and the human experience following the footsteps of our founder, Dr. Felicitas Goodman, anthropologist. And as an educational institution, we take an open approach, and we invite scholars in related fields to help broaden the scope of our own work and exploration, and that's why we call this Conversation for Exploration. And on these weekly Sunday discussions, we've had a full spectrum of topics, including neuroscience, anthropology, archaeology, art history, mythology, archaeoastronomy, much more. You're welcome to visit our website at cuyamagainstitute.com. All of our presentations are free, and as a nonprofit, of course, we invite you to become a supporting member, and we thank you, the community members who continue to support the mission of the Cuyamaga Institute. Today, let's talk a little bit about how modern discoveries in science is not only expanding our knowledge of the universe that surrounds us, but might be the key element to broadening our relationship with the universe. On this program, we recently had a panel of astronomers who first established the incredible impact and success of the Hubble telescope in expanding our perception of this most magnificent cosmos we are directly a part of. And also they shared their excitement of the launching of the James Webb telescope, which is expected to go way beyond the range of Hubble, out as far as
gathering information.
Exactly. Yeah, revealing how stars looked about 13 billion years ago. So this all affects human experience. We also had another recent guest, Bill Halal from George Washington University, who offered us evidence-based research that there's an emerging global consciousness. And he says that we have a path forward with a vision of sustainable and prosperous world.
And it's really part of our whole evolutionary track from the Big Bang to now.
Yeah.
So, yes, I have to say Happy Mother's Day.
Right.
Happy Mother's Day to all moms everywhere and to our own planet, Mother Earth. And this is a celebration of moms today and the feminine wisdom. And our quest has always been to examine our worldview, to answer those eternal questions. Who are we? Where did we come from? Where are we going? And what's it all about? To expand the story that we tell ourselves, because that's the foundation upon which all operates, about the cosmos and our place in it, to better fit our experience, our past, present, and future, the big picture. And of course, cosmology affords us one of the biggest views on these questions that we have, and our recent technology has certainly pried open the bandwidth. Cosmology is at its best when it tells us something, well, cosmic, about ourselves. And our guests today certainly do that. Their message is about the hope, the solutions, and the responsibility that this knowledge brings to write our course. And it focuses on that very worldview, the story that we tell ourselves about who we are in the grand scheme of things. And it's time for an update on that story. Joel Primack and Nancy Ellen Abrams, husband and wife team, want to say welcome. They join us today. Joel is a leading cosmologist. He started out as a theoretical particle physicist and helped create the Standard Model there, studied the formation and evolution of galaxies, simulating and visualizing the evolution of the universe with computers and galaxies under various assumptions, principal originator and developer of the theory of cold dark matter, studied the nature of dark matter, the biggest slice of matter that we cannot detect. He's worked with leading planetariums to help make the invisible universe visible, worked to bring spirituality and science together as an advisor and participant in the Science and Spiritual Quest Project, chairman and advisory committee for the AAAS program on dialogue on science, ethics, and religion, in addition to over 200 technical articles in professional journals with his wife, Nancy Ellen Abrams. He wrote The View from the Center of the Universe, Discovering Our Extraordinary Place in the Cosmos, and The New Universe and the Human Future, How a Shared Cosmology Could Transform the World, part of the Terry Lecture Series. And Nancy also wrote A God That Could Be Real, Spirituality, Science, and the Future of Our Planet, where she asks, could anything actually exist in the scientific universe that is worthy of being called God? Key question. She is a philosopher of culture and science, striving to put the discoveries of modern cosmology into a cultural context. As a musician, to communicate their possible meanings at a deeper level. She's a lawyer, don't hold that against her. She is an activist engaged in the role that science plays in shaping society, involved with scientific mediation, informing government on policies around science, its implication and impact. Welcome. What illustrious careers.
We had to shorten your bios. We're going to run out of time. But,
yeah, exactly. Yeah. We always appreciate husband and wife teams whose individual work is strengthened when they work together. We know that one. And I wanted to invite Brian Tucker, a member of our community, as well as the Deep Time Network, who met you there. Brian, you have something to share on why, and thank you for suggesting Nancy and Joel today, but you have something to say on why this is such an important topic that they'll be covering in an illustrated talk today.
Yeah, again, thank you, Nancy and Joel, for joining us. I appreciate both the voices you bring. You bring a very hopeful message, one that's grounded in science, and also seeks to integrate spirituality, which I find to be very compelling. It's a compelling message that I really appreciate hearing. I think all of us today will enjoy. What I have enjoyed of your work, I saw first on the journey of the universe in the educational series. Joel, you were featured in the conversations with Mary Evelyn Tucker. And in that movie, The Journey of the Universe, it does a really great depiction of the current understanding of science in a story form that describes our origins in a compelling way. But I really appreciated both when you were present, Nancy, at the TED Talk that you gave. And what struck me was your articulation about what motivates people to change. And I was fascinated in the way that you summarized that people can actually change very quickly to become the larger person that they are, but not by necessarily only learning facts, but by discovering a larger new identity. And I thought that's just a kind of a really great summation. And I'd like to learn more about your theories on how we change in light of this information that you'll be sharing with us today. So thank you for being with us.
Okay. Thank you, Brian. Thank you.
How's that for an introduction, boy? It's so good to have you. I'd like to start with your own story, your own call to adventure. What brought you, each of you, to the work that you do? What is the spark within that you followed? Yeah.
The spark. Well, I grew up in a very unadventurous suburban life, and I could not wait to get out of it. I could not wait. And so I went to college when I wasn't even 17 yet. And I was just so excited to have something happening in my life. Also, I must say that I grew up in the 50s. And let me tell you, I did not know a single woman who had a job, not one. Every woman I knew was a housewife, and that was it. So, and I couldn't imagine that. So I remember my very first year in college, I was at the University of Chicago, and I audited a graduate course, because when you're 17, what do you know? So I audited this course in Plato's Republic. Why? Because I thought, how could there be an entire course on one book? Okay, so that was my sophistication. Yeah. So it totally changed my life. The questions that were raised in Plato's Republic have been the questions that have occupied me ever since. How do you run a country? What is it really all about? Who are we? What are we as human beings? And how can we live together? Clearly, Plato didn't actually have the answer. I mean, philosopher king is a great idea, but we don't know how to get one. After college, I just wanted adventure. I really had no concept of a career because, as I said, I'd never seen a woman with a career. So, but I knew about adventure. So I went to Europe and I stayed for several years. And what I did, I traveled around, I learned Italian. I joined a cabaret troupe and we sang with them for a year. We did political satire. And then when I came home, I discovered there was a women's movement. It was 1971. And it hadn't been happening when I left. And suddenly there it was. It was so exciting to me. And then I decided I'll go to law school. And so I did. And I hated law school, but I did get through it. And I have to say that I couldn't even imagine staying there in the law. I could not even imagine that. I went back to Europe after that. I got a Fulbright. I went back and this time I spent a year, because now I was a lawyer, I spent a year at the first international environmental protection think tank in Europe. And it was the first time people were really starting to think about environmental problems and how they crossed boundaries. And in, Europe the countries are small relative to us. And so everything is international. So that also tremendously opened my eyes to the situation of how do we run a world that is safe and sustainable. So I came back, I ended up, I worked for a little while at the Ford Foundation, trying to help them figure out how do you resolve disputes without using courts. And that's how I got into mediation, especially environmental mediation, where there are cases where there are multiple sides and you can't just use a court to decide it. Eventually, I ended up working on the staff of Congress in their science advisory office. And there I was really exposed to all of the big science political issues of the time. The question about energy. We knew in the late 1970s that the Earth was warming. We knew that our path was unsustainable. We knew we were headed for peak oil. We knew all these things in the 70s, but in Congress, we were not allowed to think far ahead. And my office, which was called the Office of Technology Assessment, we thought a maximum of 30 years ahead, which was at the time considered luxurious and ludicrously unrealistic because people always thought it had till the next election. So you know what, those 30 years have passed and none of those problems were solved because we could not think farther ahead. At that point, while I was there, that's when I met Joel. And Joel and I met, interestingly, when we originally met when I was still at the Ford Foundation, and the President's Science Advisory Committee was trying out this idea called a science court. And what they wanted was, whenever there was a big political issue that had some sort of scientific background, which almost everything does, they would have scientists run their own special court where they would have advocates for both sides and scientist judges. They would decide what's the scientific truth today for the purpose of making the decision, and then just hand that over to the government. And so I was invited to observe a meeting that Joel was also invited to observe. I was coming from the Ford Foundation, and he was a friend of one of the scientists on the committee. And I listened to this and I thought, this is the stupidest idea. I cannot believe they don't understand either courts or science. You can't decide what the scientific truth is, and you can't run a court like this where no one has a protocol. There's no procedure. Nobody knows what they're doing. So the only person who stood up and said, this is really probably not a good idea, was Joel. So that's how we met each other at that thing. Later on, I actually proposed a better alternative, which was called scientific mediation, which you mentioned, and which has been used in Sweden, but not yet in the United States, to figure out what's the science how do we plug science into policymaking decisions? Anyway, eventually, we got married. I moved out to California, where Joel already had tenure at UCSC. And almost right after we got married, Joel started moving from physics into astrophysics. He got really interested in dark matter. And the whole, I guess it's God, 40 years now that he's been developing this theory. I've been watching and learning it and thinking, what does this mean for the rest of us? We are not living in the universe that we all grew up thinking we were in.
Mm-hmm.
And the universe is what defines reality for all of us. What does this mean? What do we do with this astonishing series of discoveries that he and his colleagues and lots of other people around the world are making? So we talked about this a lot, and we wanted to figure out a way to explain it. So it turns out that if you want to explain something, the best way to do it is to teach it to a group of skeptical undergraduates. So that's what we did. We decided to have a course, and we called it Cosmology and Culture. And we looked at the connection between the way that different cultures, so the historical part was mine, of course, and we looked at the way that different cultures have looked at cosmology and how it affected their politics, their economics, the whole way they developed. And how is that going to happen in our time? So that course, after we taught it for 10 years and really tried to hone these things, that turned into our first book, The View from the Center of the Universe, which you mentioned.
Yeah.
So after that, we got invited to give a series of lectures at Yale called the Terry Lectures. And that was published as our second book, The New Universe and the Human Future. And then, I have to say that every time we gave talks about this, and we must have given 100 talks between those two book tours, it was a lot of talks. Everywhere we went, sooner or later, somebody said, but do you believe in God? We were not talking about God. We were talking about the universe and how we as the human species fit into it. But this automatically elicited the feeling of spirituality in almost all people who came to talk. So that became a kind of obsession for me to figure out how to answer that question. And so that became my book that I wrote without Joel, because Joel is a scientist and he's not going near this. but so that became my book, which was called A God That Could Be Real. And that is a rethinking of the whole idea of God for the kind of world that we actually live in today, the kind of disasters we're facing, the need for unification, for cooperation that we have today. How can we use the concept of God to help us rather than divide us? So that's my story. And
Great story.
Yeah, thank you. Yeah. Joel, forgot to mention you were a professor.
Well, briefly, I was an undergraduate at Princeton. And in fact, I was the valedictorian of the class of 1966. I then did graduate work. Maybe I should mention, my senior thesis at Princeton was the creation of the modern theory of nuclear fission. The old theory, it's called the liquid drop model, was the work of Niels Bohr and John Wheeler. Wheeler was my freshman teacher at Princeton, a remarkable course. So he was the grader of my senior thesis. And the point of the senior thesis was this most famous paper of his and Niels Bohr's was completely wrong. And I convinced him of that, which I guess is partly how I became the valedictorian of the class. I did my PhD at Stanford, basically helping to create the modern theory of particle physics, the so-called Standard Model. And I continued that at Harvard as a junior fellow of the Society of Fellows, a glorified postdoc. When I finished my 3-year postdoc at Harvard, I remember that I didn't have to apply any place. I had offers every place across the country, 3 offers in New York City alone of assistant professorships. I ignored all of them. I'm a Californian and I wanted to come back to the Bay Area, which I'd fallen in love with at Stanford. So the choice came down to Stanford versus Santa Cruz. And I fortunately chose Santa Cruz for complicated reasons. Basically, the Stanford physics department in those days was nutty. Santa Cruz turned out to be a wonderful choice because it was already at that time one of the great centers for astronomy. The University of California's Lick Observatory had moved to the new campus at Santa Cruz when it was created. And that was the nucleus of one of the great astronomy departments in the world. And particle physics by that time had become quite boring in the mid 70s. There were going to be no important new accelerators and no important new discoveries from particle physics experiment for many years, which unfortunately has continued to this day. The main thing we've learned from the Large Hadron Collider is that yes, the Higgs boson exists. That was the missing piece of the Standard Model. But very little else, unfortunately. But astronomy was then filled with all kinds of new information, and it was clear that the amount of new data was going to grow exponentially. And in particular, Sandra Faber at UC Santa Cruz, a young astronomer, and her collaborator, Jay Gallagher, had shown convincingly that most of the mass in the universe is some invisible stuff called dark matter. Their 1979 article in Annual Reviews of Astronomy and Astrophysics was very convincing. And that really changed the attitude of most astronomers. And so then the question was, so what is this dark matter and how does it affect everything? How does it lead to the universe that we see today? So starting in 1981, I worked on this with Heinz Pagels, and we proposed what's still one of the favorite ideas for what the dark matter might be. It's called a weakly interacting massive particle, a WIMP. What we proposed was that it's the lightest supersymmetric partner particle. So it's connected to superstring theory. We don't know if that's right. We don't know what the dark matter is yet, but that then led us to work out, well, supposing that something like this is the dark matter, how would that affect the origin and evolution of the universe? How would galaxies and clusters of galaxies and cosmic voids and that sort of thing, how would that all form? So we worked it all out. We sort of lived in this imaginary universe and then publishing papers starting in '82. And in 10 years later, 1992, NASA's Cosmic Background Explorer satellite, COBE, discovered that there are fluctuations in the temperature of the heat radiation of the Big Bang. It's almost exactly the same temperature in every direction. But with very precise measurements, you can see that some regions are a little bit cooler and some regions a little bit hotter. And our theory had actually predicted that. And the agreement with our predictions was spectacular. So it was almost a religious experience, realizing that this imaginary universe that we were exploring in our theoretical papers was the real universe. There are actually several different variants. We didn't know how much dark energy there would be, as well as dark matter. So one of my graduate students worked with us to work out 96 different variants with different amounts of dark matter and dark energy and hot dark matter, as well as cold dark matter and so forth. Very quickly, we realized there were really only two choices, and one of them turned out to be the one that we now know today, which I'll tell you about in the talk that we're about to give. And I've continued to work in astronomy and astrophysics in many different areas. I'm a theorist. The great thing about being a theorist is all you have to do to work in a new field is read a bunch of papers and sharpen your pencils. But there's not a lot of equipment that you need to buy. Of course, you do have to get grants and especially get access to supercomputer time, but I've been very successful at doing that.
Yeah, from the micro to the macrocosm, indeed.
Right. But as you mentioned in the introduction that you read about me, one other thing is that I've worked almost all the time on science and policy and sometimes science and religion. As a graduate student, I helped to start something called Stanford Workshops on Political and Social Issues, SWOPSI, which continued for more than 20 years. And one of those first workshops, which I co-led with Bob Jaffe, who was also an undergraduate at Princeton and also a valedictorian, and he worked with the same thesis advisor as I did. We sometimes even worked together on physics. But he and I and Joyce Kobayashi, the student body president, started this program of courses whose goal was to change the world. And in some cases, we succeeded. So the course I was involved with helped to create the Congressional Science and Technology Fellowship Program. We did a questionnaire of Congress with the help of congressmen and senators. And it was clear that that was something that would be favored by Congress. And so I got a chance to get that started, working with the American Association for the Advancement of Science, AAAS, and the American Physical Society. And thousands of scientists have now worked in Congress, and the program was expanded into the executive branch as well. That's about 200 to 250 scientists a year, PhD scientists. So this has had a big impact on the scientists and occasionally maybe even on the government. And I also was heavily involved in a number of other programs on science and technology and religion.
I just want to say it's very exciting that you're looking at and bringing home all this knowledge and how it affects all of us, and that you're looking, how do we correct course? We have to look at not just the fundamental particles of creation, but the fundamentals of the story that we tell ourselves, because that shapes everything. The worldview, the paradigm. We shape that, and then we shape our course. And that involves all of us, right? That's a very empowering place to be. And to update that, I mean, that for me is the real key question, right? Who are we in this grand scheme of things? What is our responsibilities and our roles? So, and this is something that we've been looking at. We're looking at the past. What is the wisdom of the past that we can carry forward? What is the wisdom of the future? What are we finding out to shape this and steer the wheel?
So that's indeed the structure of our talk.
Yes, thank you. So let's begin.
So let's share screen and show you our slides. Very good. Okay, so that's the title slide. And why don't you take it from here, Nancy?
Okay. Well, I'm going to introduce this because Joel's going to get into it a little bit more technically later. But what I want to say is that we have the first opportunity today in 400 years to re-envision the universe. And this is so rare, I can hardly even tell you how rare it is, except to show you exactly how our pictures of the universe have been changing over the last, shall we say, 3,000 years. There were only 2 or 3, depending on how you define the major shifts in the view of the universe in the past 3,000 years. So there have been thousands and thousands of origin stories and so forth, but the fundamental view of the universe has not changed often at all. So this is the point of view that so many people have this today that, as you can see, even children have it. So Lucy says to Snoopy, "You are of no importance. Did you know that? You're only the tiniest speck in an enormous universe." And Snoopy just thinks about it. Well, I might as well go back to sleep. Because there's nowhere to go with that. And here's the exact same thing in Calvin and Hobbes. So Hobbes says, "What a clear night. Look at all the stars, millions of them." And Calvin says, "Yes, we're just tiny specks on a planet particle hurling through the infinite blackness." And they think about that for a second. Let's go in and turn on all the lights. The idea being, we are insignificant. It's huge. It's scary. I don't really want to think about it. Let's not pay attention to it. This is the point of view that people have today. Okay, let's go to the next one. So what I want to talk about is, what is a cosmology anyway? What does it even mean? And this is the outline of our whole talk. Then we're going to explain what is the scientific cosmos. And the way we're going to do that is to introduce to you 3 images that Joel and I have designed to represent fundamental concepts of this modern picture. It's one thing to try to we're obviously not going to use equations, but it's also almost as difficult to understand some sort of didactic explanation of how the universe works. So what we've done is we have created symbols. And if you can understand the symbol, once you understand the symbol, the whole idea can take shape in your mind. And then you can see that there is no one way of representing the universe. But if you represent each of the fundamental principles of it and realize that the universe has all these different angles, then you start to comprehend how to even think about it. And one of the things you discover in doing that is that Earth is a very special planet. Earth is absolutely extraordinary in this cosmos. And we will see that human beings are central, not geographically central. There's, of course, no geographic center to an expanding universe, but we are central to the fundamental concepts underlying this modern picture. And this was a discovery. This was not something we expected to find. This was something that we discovered. And we kept discovering new ways that were central. And that's what led us to write our book. So why are we talking about this? How isn't the universe just way out there and not really of interest every day? Well, we can find meaning in this new picture if we choose to. Nobody can force you to find meaning in it. Nobody can force you, but when you realize where we are and you can find the meaning in it, then you find a place for yourself in the universe that you cannot possibly have imagined before. And let's go to the next one. So let me start by explaining what some of the really ancient cosmologies, I'm going to do this very quickly, showed. In the ancient world, the idea was the Earth is flat. And we don't know how many thousands of years people believed that before. Probably most indigenous groups believed the Earth was flat because that's how it looks. So anyway, this is a very, very ancient picture of the goddess Nut, who held the stars in her body. I'll give you a simplified version of this because all these Egyptian pictures take hours to even just figure out what's in them. So let's just go for the really important part. So here what we have is three gods, and their names are Nut. She was the cosmos, and the stars were in her body. Geb was her brother and twin. And according to the mythology, they were born together in a loving embrace, and their father, Shu, separated them and made the heavens and the earth. The idea of Nut was that every morning she gave birth to the sun, and every night she swallowed the sun, and it traveled through her body in the darkness. So there was no light from the sun anywhere during the night. That's the idea, was that the sun was dark during the night, renewing itself, and then would be reborn in the morning as the sun. Now, this was a flat earth picture where all the parts were gods. The earth was a god, the air, Shu, was a god, the heavens was a god, Nut. Now, when the Hebrews came along and they were trying to sell the idea of monotheism, that there was only one God, they had the same exact picture, but none of these parts of it were God. The parts now became inanimate, and Geb became the dry land, and Shu became the space in between, and the firmament was Nut. Although actually the word firmament was only invented for the King James translation of the Bible, in the Shakespeare's era. It actually in the Bible, it's just called a hard thing. The idea being that there was water everywhere in the beginning, and whatever God you believed in at the time separated the waters so that there would be a space in the middle for the creation. So in the Bible, it says God created a hard thing, which was this dome that held up the cosmic waters, and the dry land was flat. So you can see that these are basically the same picture, except the Hebrew one becomes inanimate.
Separating waters instead of the gods. Yeah.
separating the waters. In fact, you know, people have been reading Genesis forever, and they never really understand. Most people do not understand what happened on day 2 when God separated the waters. What did that mean? God separated the waters. People think, oh, that means he made rivers and he made the, no, that's not what it means. It means that there was water everywhere. And to separate the waters, God had to lift the cosmic waters, and they stayed up there until the story of Noah, when God opened the windows of the heavens and allowed the cosmic water to come in. And that's what destroyed the earth in the Noah story. But unless you know the background of what the cosmology was, you can't really understand that story. Okay, so let's see what happened after this. The Greeks were the first to propose that Earth was the center of the universe and it was round. This was huge because this went way beyond observations. They really figured it out with theory. And as the Greek idea developed over the Middle Ages, and it lasted for more than 1,000 years, the medieval picture became that Earth was the center of the universe. Let me just point to this. Here we are. Here's Earth. Earth is the center. Oh yeah, is it on the next page? Oh yeah, here's a bigger picture. All right, so Earth is the center of the universe. And then there are these concentric spheres, which were supposed to be made of crystal, so they were invisible. Earth, and then the moon was in the closest in sphere, and then the planets Mercury and Venus, then the sun, which had its own little sphere, Mars, Jupiter, Saturn, those were all the planets that were known. And then they believed that on the outermost sphere, all the stars were affixed to the sphere, and that's how they could appear to go around the Earth every day. Mm-hmm. The Earth didn't move. The Earth was the solid, stable center of the universe. And this is how it was until the time of Galileo. So then, we're using Newtonian, but the change started with Galileo.
And Copernicus.
And Copernicus, of course. And so the next picture of the universe, the next cosmology, and we're talking about, this is only the third cosmology in the entire history of Western civilization. Flat Earth, Earth at the center, and now Earth as a moving planet. That was it. And all of these pictures are wrong. I mean, this picture is locally right. The Newtonian picture is locally right, but it is not a picture of the universe. It's only a picture of our solar system. And the philosopher and religious leader Blaise Pascal, when he first heard the idea that Earth was a moving planet and that there was no outermost sphere. See, the reason that the outermost sphere of stars was important in the Middle Ages was God was right outside it. That gave a place for God. We were immersed in God. The whole universe was immersed inside God. And there was even a theory that what the stars was holes where the light of God was shining through on us. So you can imagine just the sense of feeling of belonging, of knowing your place, when every time you looked at a star, you could think it was the divine light shining on you. Well, that disappeared with Copernicus, Galileo, and Newton. And Pascal said, I feel engulfed in the infinite immensity of spaces whereof I know nothing and which know nothing of me. I am terrified. The eternal silence of these infinite spaces alarms me. And there was a lot of pushback against this Newtonian picture because it really destroyed the whole sense that we fit into the universe. We had no place at all now. So we are now in the next shift away. As I said, there were 3 pictures before ours. This is only the 4th picture. And here's the big difference. This is the first picture of the universe that might actually be true. It's the first picture of the universe ever based on evidence. And that's the big difference. I mean, it's true that the solar system picture was based on evidence, but very, very limited evidence. Now, these are the 4 pictures that we're going to that we're going to explain in this talk. And each of these is a symbol that represents a huge amount of information, but that can be boiled down. Now, why do we really need this? Why do we need this new cosmology as human beings rather than just as scientists? What did it take to build the pyramids? It took people, it took a vision that was shared over generation after generation after generation, century after century. The same thing was true of the medieval cathedrals. These enormous undertakings that are so iconic of human culture took many generations to do. And the only reason that was possible was that people shared a vision and they held on to it for a long time. We don't have anything like that today. We have nothing like that. Every religion has its own story. A lot of people are not religious. A lot of people are cynical. I mean, there are new age ideas of, vague energies that can't be defined in any way. That we have simply no picture, and we have no underlying political ideology either that would hold us together, that would allow us to collaborate. We can't do big things like this the way that we think now. If we want to ever explore space, if we really want to be able to move off Earth and see what's going on in the rest of the galaxy, and can we do space exploration, this is going to be a many, many generational project. We can't do that the way we think today. A couple of big egos like, Elon Musk and Jeff Bezos, they can't do this kind of thing. This is a big cultural undertaking, space colonization. And if we ever want to do it, and even if we don't want to do it, but even if we wanted to be able to do it, we need a unifying vision. Even to deal with climate change, we need a unifying vision. To do anything on a global scale, we need that. And what our talk today is going to be is basically a foundation for that kind of a vision. It's not a complete vision, but it's the foundation for the vision. If we're ever going to have a shared vision, it has to be based on what's true for all of us, what's true for everybody on Earth. And the only thing we know that's true for everybody on Earth is science. It's not going to be based on anybody's current religion. It's not going to be based on any political ideology of the day. It's got to be based on the truth. And that we can build on. The truth is not alone. The scientific truth is certainly not adequate for a cosmology. Because a cosmology, well, let me just digress here for one moment. The cosmologies of ancient times were not just pictures of the universe out there. They explained how we as humans fit in, what the gods expected of us, what morality was. It was a complete big picture. Obviously, it wasn't right. It wasn't accurate by scientific standards, but it held each culture together. And that's what we need. But now it has to be based on this complicated, but definitely understandable cosmology that we're going to explain now.
So, as Nancy said, we're now creating humanity's first picture of the universe that might actually be true in the sense that it has scientific support and is unlikely to be overthrown. And surprisingly, in this new scientific picture, we're cosmically central and we live at a pivotal time. And that's what this next part of the talk is going to explain. So beyond the solar system at the top, on a larger scale, we're showing the Milky Way galaxy. And the bottom of that triangle shows that we're about halfway out from the center to the edge of the Milky Way galaxy, about 25,000 light years from the center, 25,000 light years from the edge, about 100,000 light years across. That's the visible Milky Way. The Milky Way is just one of two big galaxies and hundreds of small galaxies in the local group of galaxies. And if the video that we're going to show in a minute works, we're going to take a trip from our local environment, in the Milky Way across thousands of galaxies to the center of the Virgo cluster, the largest concentration of galaxies in the nearby universe. That's still very small on the scale of the universe as a whole, which we'll talk about later. So we're going to start heading toward this familiar constellation. I hope everybody recognizes it, but just in case you don't, there is the belt stars, the three belt stars, Betelgeuse in the upper left, Rigel in the lower right. This is Orion. So here we go. So these are all, these stars are put in the correct positions based on our scientific measurements of exactly where they are. That's the Orion Nebula. Nebula is just a glowing gas cloud. There's some dark dust that makes the shape of a horse head. This music, incidentally, is by Nancy. Among other things, Nancy is a composer and a singer-songwriter. This is the Rosette Nebula, another stellar nursery where new stars are born, like the Orion Nebula. So nebula just means a glowing gas cloud. Here's another glowing gas cloud, but this one isn't a star birthplace, it's a star death place. This is where a star blew up in 1054 AD, as we saw it. The Crab Nebula, it's called, and there's the flashing neutron star in the middle. To really see our galaxy, you have to move up and out of it because the view toward the center is pretty much blocked by dust created by explosions like the Crab Nebula. So this is what a magnificent galaxy like ours looks like. As it recedes into the distance, we see the two big satellite galaxies, the Large and Small Magellanic Clouds on the left there. And now the other big galaxy in the local group comes into view, the Andromeda Galaxy. There's a smaller spiral galaxy, a Triangulum Galaxy. It's about 2 million light years away. And we're going to go through a nebula in the Triangulum Galaxy now. Now we're going to take a scenic route to the Virgo cluster. Notice that the galaxies are not randomly distributed. Notice how they're stretched out along lines, filaments that we call them. This is a particular favorite of mine, the Whirlpool Galaxy. All right, now we're going to join that filament that heads into the Virgo cluster. So we're moving into it. Now we're going to go down. Okay, well, here we are at the end of our voyage at the center of the Virgo cluster. This big galaxy at the center has a jet coming out of the black hole in the middle. This galaxy is one of the biggest nearby galaxies, M87.
Why does it look so different from the others?
Oh, well, it's an elliptical galaxy. It's quite large. It was formed by a number of galaxies colliding together. And the consequence is that the stars go more or less randomly in every direction, not like our galaxy and the Andromeda Galaxy, where the stars are mostly in a disk rotating around the center. So this is what a galaxy looks like to an astrophysicist. Right in the center is the visible galaxy, that 100,000 light year thing. But surrounding that on a scale at least 10 times bigger in all three directions, so 1,000 times the volume, is the dark matter halo of the Milky Way and other big galaxies. There are dense regions in the dark matter halo, and those are where the big satellite galaxies are, and also some small satellite galaxies and some very tiny satellite galaxies. We're discovering more of the small ones all the time. There have been about 30 discovered in just the last few years, and many more are going to be coming as we turn on new telescopes. How does this fit into the large scale structure of the universe? More or less like this. So this is from one of the big computer simulations that Anatoly Klipin and I ran on NASA's big supercomputer, one of the biggest in the world, the Pleiades supercomputer. And what you see is that the dark matter is very filamentary. The galaxies tend to lie in these dark matter halos, we call them, big blobs of dark matter. Those are the yellow dots. The big yellow dots are the dark matter halos for groups and clusters of galaxies, where lots of galaxies fit together. And this basic filamentary structure is what that video is supposed to be showing you, that the galaxies really are strung out along these long lines. Now, here's that cosmic spheres of time that we were talking about. The material before was kind of introductory to that. As we look out in space, we look back in time. Because if we want to see galaxies that are far away, the light must have left them a long time ago when the galaxies were at an earlier stage of evolution. So the center is us. The first sphere is about 4.5 billion years out. These are spheres of time, remember, and that represents the sphere from which we're just receiving light that left when Earth formed.
Okay.
Now, the galaxies around that look very much like the galaxies nearby. Galaxies haven't changed that much in appearance in the last 5 billion years. But if we go out to 10 billion years, when the big galaxies are just forming, then you start to see some galaxies that look strange. Notice this odd-looking galaxy. And when you go out beyond that, all the galaxies look strange. They're usually sort of elongated, and they have bright dots in them. We call those clumps of stars. That's as far as we can see with Hubble, but James Webb is going to let us see considerably farther, closer to the Big Bang itself. So the cosmic dark ages are going to get a little bit less dark because of Hubble's, because of James Webb Space Telescope's ability to see light that is redshifted, that's gotten very long in its wavelength, and that we couldn't see with the best cameras we had on Hubble. We can see much farther with James Webb. It's also a much bigger telescope. The colorful sphere is the cosmic background radiation, and the different colors simply represent slight differences in temperature on the millionths of a degree scale, which we can now measure quite accurately. And then finally, the outermost sphere is the cosmic horizon, the Big Bang. We can't see beyond that because time didn't exist beyond that, at least not in our sense.
Nothing to see beyond that. Yeah.
Right. And in fact, the universe isn't transparent to light beyond the colorful sphere. But we could see gravity waves from beyond that, and we may very well do that very soon in the next few years.
Oh.
So here's a picture, sort of iconic picture from Hubble, called the Hubble Ultra Deep Field. It's beautiful, but it's misleading since it only shows half of 1% of what's out there. The other 99.5% of the universe is invisible. And that's been a challenge for us astronomers, because we've had to try to figure out the whole story, only being able to see half of 1% with our eyes. So without going into the details of how we know these things, let's summarize what we know about the contents of the universe in this other iconic symbol, a pyramid. So most of the density of the universe is something we call dark energy that makes the universe expand faster and faster. The next biggest component is cold dark matter, about 25% of cosmic density. And that's what holds galaxies together and clusters of galaxies and so forth. On larger scales, the dark energy is winning and making the universe expand faster and faster, moving those things apart. It doesn't make the galaxy expand. The galaxy is held together by dark matter, but the space between the galaxies is expanding very rapidly. The 5% or so of atomic matter, matter made of protons, neutrons, and electrons, the stuff we're made of, is mostly invisible. Only about 0.5% is visible of the total density, about a tenth of the ordinary matter. And it's practically all hydrogen and helium that came out of the Big Bang. And all the other visible atoms, the carbon and oxygen and stuff that we're made out of, in addition to hydrogen, is about 1/100% of cosmic density. Let's zoom in and look at that. And of course, we borrowed this symbol from the back of the dollar bill, the Great Seal of the United States, which we slightly reworked here. The bottom part represents hydrogen and helium, and the first stars are made exclusively of hydrogen and helium. And then those stars and the stellar processes they're involved in make all the other atoms, which come out as stardust. So the entire periodic table is made, except for the hydrogen and helium at the top, by stellar processes. This is the latest thing we've learned about the origin of the elements in the periodic table. When the first stars formed out of hydrogen and helium, we have good reasons to think they were very massive, perhaps 100 times as massive as our sun. They would have lived only a few million years. And when they ended their lives as supernovae, they became neutron stars or even more massive black holes. We've now been discovering the gravity waves emitted as these black holes collide. And you can turn those gravity waves into sound. It sounds something like this. The chirp is the gravity waves that represent the merger of two massive black holes. So these were first seen in 2015. In 2017, the two American gravity wave observatories, LIGO, were joined by a European one called Virgo. And they together discovered gravity waves emitted from merging neutron stars. And once we were able to point big telescopes at that neutron star merger, we found enormous amounts of very heavy elements like europium, gold, thorium, and uranium, about 10 times the mass of Earth, just in gold. Whenever I see somebody wearing gold jewelry now, I think, I know where that came from. Some neutron star merger. So this is that periodic table of the elements, the current version from a recent issue of Science magazine. And the orange part represents the elements, the fractions of the elements that were made by these merging neutron stars. Notice thorium and uranium on the bottom, elements number 90 and 92, entirely made by merging neutron stars. Also, iodine, number 53, iridium, number 77, europium, number 63, almost all made from merging neutron stars. Okay, so to summarize our picture, again, with that pyramid, now redrawing the pyramid the way Nancy imagined it one clever time. Imagine that the entire universe is an ocean of dark energy. That's that 70%. On that ocean sail billions of ghostly ships made of dark matter. But you don't see the ocean and you don't see the ships. All you see are the beacons at the tops of the tallest masts of the biggest ships. Those are the galaxies. And that's the visible 1/2%. So dark matter ships on a dark energy ocean, that's the matter and energy content of the universe as we now understand it. The standard name for this theory is lambda CDM. Lambda, what Einstein used to represent dark energy, the cosmological constant is the simplest version. CDM, cold dark matter, the theory that I helped to inaugurate back in 2002. So,
No, it's
sorry,
1982.
1982, not 20 years ago, 40 years ago, as Nancy said. So this is the double dark theory. That's what we call it in our popular books and lectures, because it's based on dark matter and dark energy. Okay, well, moving on to the size scales of the universe. Nancy, why don't you take over for a little while?
Okay, so it's almost impossible to find, it is impossible to find language to explain size. You can say things like huge, but does huge mean huge like a mountain? Or does huge mean huge like a galaxy? It doesn't mean anything. So what we've done here is we have arrayed all the possible sizes that things can actually be around a serpent swallowing its tail. You probably noticed that we repurposed that medieval picture to be the cosmic spheres of time, because these ancient symbols really have tremendous resonance, and it's really much better to reinterpret them than to try to invent something from scratch that has no resonance whatsoever. And there's no reason not to do it, especially with this symbol, because the serpent swallowing its tail has been a symbol of the cosmos in hundreds of different cultures, and it hasn't meant exactly the same thing. So, for example, in the Norse culture and also in the Huichol culture, it's the horizon of the world, coming back, of course, to the idea that there's a flat earth and there was the serpent around it. In other cultures, it's meant the infinity of time that goes round and round, but it's always something huge and cosmic that it symbolizes. So what we've done is we have just repurposed it yet again to mean all the sizes. And I have to preface this by saying that there is a largest and a smallest size that things can actually be in our universe. Numbers go on forever in both directions, but not in the physical universe, because there was a beginning to this universe. And the biggest thing that we can see is the horizon of the universe, because that's how far time has allowed light to come to us from. So on this, what we call the cosmic Ouroboros, Ouroboros literally means in Greek, tail swallowing. The tip of the tail is the smallest size that physics can say anything meaningful about. It's called the Planck length. It's 10 to the minus 33 centimeters. It is a theoretical number. And the largest size that we can say anything about is the cosmic horizon, the size of our visible universe. There may be something beyond it, but we can't say anything meaningful about it. So there we go. There's the top and the bottom in terms of sizes. And then going around the Ouroboros, let's start from here. This is a supercluster of galaxies on the scale of 10 to the 25 centimeter. This is the size scale of a single galaxy. This is the size scale of the distance to the stars in Orion. This arrow represents the little trip that we just took in the video across the supercluster. So we started out at Orion and we went to, you could see the size of the supercluster in it. So, all right, so keeping on going around the Ouroboros, this is the size scale of our solar system, the size scale of the sun, the Earth, a mountain, people, an ant, a single-celled creature, a DNA molecule, a single atom, the nucleus of an atom. And then there are some these exotic particles that that represent the forces that hold atoms together. And possibly the dark matter is in this, but of course we haven't discovered the dark matter yet, so we don't know exactly how large it is. So the idea is that this is the entire universe from the point of view of size. This one doesn't tell us what the universe is made of. That's what the pyramid showed us. This is why we have to have different symbols for different fundamental ideas. So now, what does this mean? What is this blue thing? And I named this section of the Ouroboros Midgard, because this is the section that we live in. This is the section for which human beings have always had intuition and have been able to observe. And I chose the word Midgard because Midgard was the island of human society in the Norse myth. And the idea was that
Norse hang out, yeah.
In the Norse point of view was that the universe was a sea, a great sea, going back to that ancient idea that there was water everywhere. It was a great sea. And our island of Midgard was in the middle. And off to one side was the land of the giants. And off to the other side was the land of the gods. So this is actually very interesting when you look at the cosmic Ouroboros to think of it this way, because here we are on the island of size scales that are meaningful to us, but off in one direction here is the land of the giants, things as big as galaxies and superclusters, things we can barely wrap our minds around. In the other direction is, I'm not going to say this is the land of the gods, although sometimes I like to call this the we gods, the WEE gods, because the tiny things, the cells that make us up and the atoms that make cells up are far more fundamental than we are. They really are the source of what we are. So if we think of this as the land of the we gods, then we really are on this island in the middle. And I think that every time we find a way to see how we fit into the universe, it's really valuable. Now, notice where humans are on this. These are all the sizes that are possible, and we are smack in the middle. Why? This is such a special place, because if we were very much bigger, like we were big as a galaxy or something, we couldn't think. We wouldn't have had time for more than a few thoughts in the entire age of the universe. But if we were much smaller, then we wouldn't be made of enough atoms to have the kind of consciousness that has emerged in us. So really only somewhere around the middle of the size scales of the universe is it possible for intelligent beings to be able to think. So this is true not just of us on Earth, but really of aliens anywhere. They have to be more or less our size range. I don't mean like, 5 or 6 feet tall, but somewhere, shall we say, between the size of a redwood tree and a puppy.
The Goldilocks theory.
Yeah. Well, the Goldilocks theory, that's us. That is exactly how we humans are turning out to fit.
I find it interesting that dark matter is conceptualized as even a tinier particle than the atomic particles. I hadn't considered that dark matter would be just a tiny particle on the scale. It's interesting.
Well, we need higher and higher energies to make smaller and smaller things. And we're hoping that when the Large Hadron Collider turns on with a higher luminosity, more events per second, we'll be able to see hints, at least, of forces that we hadn't detected before that work on even smaller scales.
To illuminate what we can't
There'll
see.
be more massive particles.
Ergo dark.
Anyway, that's one of the possibilities for what the dark matter is. We don't know, so that's why the question mark is there.
Gotcha. Yeah.
So
You can discuss.
on all these big scales, the forces of the universe really boil down mostly to gravity. On the scale at the middle, which is also the scale of the greatest complexity, that's the peak of complexity. When the human brain is the most complex thing we've encountered so far. There, the forces are electricity and magnetism. That's what holds atoms together into molecules, for example. On the scale of atoms, and especially the nuclei, the weak and strong forces are important. The strong force holding the nucleus together, despite the fact that the protons all have the same electric charge and repel each other. The weak force leading to transformations, decays of particles. And as I said, dark matter may be in this region that we're just starting to explore. And at the very top, the idea that could unify the smallest scale and largest scale that could combine gravity with the other forces, superstring theory, which is based on supersymmetry. And if that's right, then this idea that I put forward back in 1982, that the lightest supersymmetric particle could be the dark matter, may actually turn out to be true. Still to be determined. So this certainly shows you that size matters. Different forces are important on different size scales. So let's look at those different size scales very quickly, going from the scale of the supercluster, the galaxy, scale of the local stars, the solar system. Here. Here we are now.
The power of 10.
There's the DNA. There's the carbon. There's the nucleus of the carbon. And that's a fanciful interpretation of what might be inside one of the nucleons. So here we are now talking about planets. So we live, of course, on the third rock from the sun. There are 4 inner rocky planets, and then and it takes light 8 minutes to get from the sun to us. It takes 40 minutes to get to Jupiter, and about twice that to get to Saturn, the 2 gas giant planets. And then there are some ice giant planets beyond that, Uranus and Neptune. So we used to think that our system is typical, with Earth and other rocky planets near our star and gas giants farther out. That turns out not to be the case at all. We've never found another system like ours.
Really?
Of the roughly 5,000 planetary systems astronomers have now discovered, there are hardly any with the planets widely separated, as in our system, in almost perfectly circular orbits. Most planetary systems are much smaller, and the common type of planet seems to be 2 to 6 times Earth's mass. It's called a super Earth or a mini Neptune. But no such planet exists in our solar system. Most of the planets we've discovered were discovered by the Kepler satellite, and it searched that little region about 3,000 light years from us. Remember, the galaxy is 100,000 light years across.
Mm-hmm.
Some planets are in the habitable zone around their stars, which just means that on their surface, water would be in liquid form. But most of those planets are probably not hospitable to advanced forms of life. For example, most planets are close to low-mass stars, which frequently emit killing radiation. Even planets of well-behaved stars like our sun might not have an optimal abundance of the long-lived radioactive elements, thorium and uranium, to permit a magnetic dynamo, in other words, to generate the magnetic field, and the moving continents, plate tectonics. Too much thorium and uranium would result in a lava world with frequent flood volcanism, which caused the greatest mass extinction events on Earth. Our living Earth may be a rare Goldilocks planet with just the right amount of thorium and uranium. So here's an artist's sketch that illustrates. So in the center, you see Earth. The inner core is solid. The outer core, made mostly of iron, is liquid. And the inner core is very hot, and convective flows, those sort of circular things, in the outer core, the molten outer core, are carrying the heat away from the hot inner core. And the uranium and thorium is mostly in the mantle, that sort of grayish region, this region here. And if there's too much thorium and uranium, it'll make the mantle so hot that it's no longer possible to carry heat away from the inner core by these convective motions in the outer core. And it's those convective motions together with the rotation of the Earth that generates the magnetic field. So add too much thorium and uranium and you kill the magnetic field. You also will cause huge amounts of volcanism and probably render the planet
Unstable.
inhospitable to any form of advanced life. Life would be wiped out, or at least taken back to the simplest forms by these terrible events. And if you have too little uranium and thorium, probably there's no plate tectonics, and that's what recycles a lot of the most important material like carbon. So this is a discovery that my group made. We published it in November 2020 in the one of the most important journals, Astrophysical Journal, the letters part. So APJ is what we call that journal. And this shows you that if we had just a little bit more uranium and thorium, we'd be in this black zone for at least a few 100 million years or billions of years. And that's where there's no dynamo, no magnetic field. The magnetic field shields the surface of Earth from the radiation that the sun and the cosmos emits, and it would make it inhospitable to have life on the surface. And it also, the magnetic field shields the atmosphere. One of the reasons Mars has so little atmosphere is that it's no longer got a magnetic field, which it only had in its first billion years or so. And the solar wind, the particles flowing out from the hot outer layer of the sun, are stripping away the atmosphere, and that would have happened to Earth too. So that's a sort of a technical picture. Anyway, one of the things you pointed out in that paper is that we can tell how much uranium and thorium there is by looking for europium, which is fairly easy to detect in the spectrum of stars. And since the europium is almost all made by the same process, these merging neutron stars, as the thorium and uranium, we can use that to predict the abundance of thorium and uranium in the star's rocky planets and decide which planets to spend a lot of telescope time with James Webb and other new telescopes to study the planet's emitted energy to see if there's signs that indicate life. That's going to be something that we have to spend a lot of time on. So best to choose the right planets. And something that I should emphasize is about half of the total heat of Earth comes from uranium and thorium radioactive decay. So when I explained this to a friend, he said, "That's the first good thing I've heard about uranium."
Well, it's not going to be so simple to go out and terraform any old planet.
Right.
It's
It's
right
not
conditions for it.
incidentally, something like half of the organisms on Earth, of the mass of life, lives below ground, down at least as far as a mile and probably further.
Yeah.
Where does it get its energy? Not from solar energy, which is where all the life on the surface and above gets its energy, but rather from radioactive decay of thorium and uranium. That splits molecules, and then rejoining those molecules releases energy. So there's evidence that there was a gigantic rearrangement in the outer solar system that caused many comets to hit the inner planets until about 3.8 billion years ago. The solar system started 4.6 billion years ago. A primitive microbial life got started on Earth very soon after this ended. So primitive life may be very common in the universe, at least on planets with liquid water. But it took another 2 billion years for complex eukaryotic cells, in other words, cells with separate internal structures like nuclei, and then complex multicellular creatures only evolved about 500 million years ago. So intelligent life and science, which arose only once on Earth, may be very rare. So again, there's our Earth. We humans and our planet are stardust evolving into awesome complexity over billions of years in an expanding universe shaped by dark matter and dark energy. So to summarize, we live at the center of our cosmic spheres of time. The finite speed of light makes this inevitable. We're made of the rarest stuff in the universe, stardust, rarer even than neutrinos as far as their contribution to the total energy density of the universe. We live in the middle of all possible sizes, where the possibility of tremendous variety and complexity coming in small packages keeps life interesting. Life of our complexity could bloom nowhere else on the cosmic Ouroboros. Our solar system is unusual, so we live on a very special planet. Our solar system is unusual in having planets in widely spaced, nearly circular orbits with two gas giants, Jupiter and Saturn, that help to sculpt the inner planets. Earth's moon formed from a collision that helped create favorable conditions for evolution of complex life. Earth could be hospitable for hundreds of millions of years if we let it. We also live at the midpoint of time, which I didn't have time to explain, but it's discussed in our books, which is also the peak moment in the entire evolution of the universe for astronomical observation. The most distant galaxies, which we've just acquired the technological ability to see, are beginning to disappear over the cosmic horizon now that the once slowing expansion of the universe has begun instead to accelerate.
Interesting.
So we also live in the midpoint in the life of our planet. It formed along with the sun and the other planets about 4.5 billion years ago, and it has about 6 billion years to go before it's roasted when our sun swells into a red giant star. Complex life evolved about 500 million years ago and has about 500 million years to go until the warming sun overheats the Earth. Unless our descendants moved the Earth further away from the sun, which could be done by cosmic engineering. You can ask me about that, and I'll explain how it would be done.
Okay. Yeah.
That'd
And,
be fun.
then we could have billions of years. And of course, we also could move life, or at least robotic stuff, throughout our galaxy if we have a long-lived civilization, as Nancy explained. So finally, from the point of view of our species, today is late enough to have evolved our present abilities, while early enough for our descendants to have a multi-billion-year potential future. For the generations alive at this moment, it is late enough that we're sobering up to the scale of our problems, but not so late that we've lost all chance to solve them. Today is a pivotal moment that will never come again. And this is a graph from our second book that Nancy and I wrote together based on our Terry lectures, The New Universe and the Human Future. What it shows is that the amount of carbon dioxide in the atmosphere was almost exactly the same for the last 2,000 years, except for the very recent part, about 275 parts per million. And in fact, it oscillated between about 200 and 300 for the last million years or so. We have bubbles of air trapped in the ice in Antarctica that tells us exactly what the composition was over that period. And over a longer period, it was higher in the distant past. But notice how it's changed since 1800, when we started to burn coal and other things that put a lot of carbon dioxide into the atmosphere. So the red curve is the human CO2 emissions with the right-hand axis. And the blue curve is the carbon dioxide in the atmosphere. And it's pretty obvious where that's coming from. It's doubled about approximately every 30 years. And we're in the last doubling. If it doubles one more time, we're doomed. We've got to stop it on a time scale of 30 years. And we've got to get started right away.
So doubling it, if it happens and we're doomed, what does that actually mean? How does that tip the scale into?
Well, we don't know, but there are tipping points that we're very worried about. One is the release of a lot of carbon dioxide that's been trapped in the cold bottom of the ocean.
Right, the methane.
So methane and carbon dioxide could be released. They are being released, in fact, as the Earth warms. And there was a big release. We're not sure what it came from. It may very well have come from the Clathrates. It might also have been volcanic eruptions about 56 million years ago. That was the last time Earth had a superheating event. The carbon dioxide level went up to well over 1,000 parts per million. It stayed that high for about 100,000 years. It took that long for weathering to take the carbon dioxide out. Antarctica was a jungle. There was a great change in the popular life forms. And in fact, it was during that period that the monkeys first evolved. So our primate ancestors. Anyway, it would not have been good, though, for most of the species then alive. So we have to learn this inconvenient truth and stop believing reassuring lies.
Well said.
Nancy?
So what do we do with all of this? Well, so what we've got here is a metaphor of a metaphor. Okay, so this is what I'm calling the Ouroboros of human identity. And the idea here, based on the other Ouroboros, which is about size scales, is that at the smallest, we each have a self-consciousness. We know that we exist. Then at a somewhat larger size scale, we think of ourselves as part of a family. And at a somewhat larger size scale, as part of a tribe or community. And then as time went on in culture, we started identifying ourselves as part of a religion or a nationality. In other words, we started identifying ourselves as part of a larger and larger group. But now the challenge of our time is to expand our sense of loyalty and belonging to the next larger group, which is the human species. which we all know we're part of, but we don't feel it and we don't act as if we are. And then beyond that, we are also part of life. We are earthlings, and we are part, at least, of the consciousness of the cosmos. Because there aren't going to be that many conscious worlds in our cosmos. When you see the way that the universe is made and how rare our planet is, as Joel mentioned, of the 5,000 extrasolar planets that have been discovered so far, there's not a single one that's like ours. We are living on a jewel of this universe.
Yeah.
So we need somehow, as people, as individuals, we need to start having an identity that's much larger than we've had, that recognizes that we are the human species, and the fate of the human species is our fate, the fate of our children. So I think it's really important to realize that we can take some of these scientific ideas and start seeing how they affect us and how they could enlarge our thinking. Okay, so that's our talk. And
That
these
was
are the
brilliant.
books.
What a powerful, beautiful journey, and what a call to action.
So let me just mention that at newuniverse.org, you can find all the images and videos that we showed, and many, many more, all freely available for people to reuse, preferably with
Just turn. No. Push the head.
Yeah,
So
with proper credit.
Lovely
With proper
images.
credit.
actually, our daughter is calling us.
it's all right.
So we'll have
She's
to
going to
call her
wish you
back
happy
later.
Mother's Day, no doubt.
Yeah.
I think so,
Probably.
exactly.
Yeah.
And we have to
Thanks.
wish her happy Mother's Day.
Yeah.
Anyway, I just wanted to mention the newuniverse.org has lots of additional material. And then finally, there's Nancy's book. And she didn't mention that Beacon Press, which published the book, said that she should have forwards by a great religious thinker and a scientist who's written lots of popular books.
Yes.
And the scientist is Paul Davies
Yes.
from Arizona State University. And the other forward is by Archbishop Desmond Tutu.
We've interviewed Paul in the past.
Yeah. And
Yeah.
we celebrated Desmond when he passed. Thank you for the journey.
Yeah.
Somebody in the chat mentioned Ray and Charles Eames' early film from the 70s, The Powers of 10, and yeah, I've seen that, and that is really stunning. And Buckminster Fuller, that tried to pull back and look at one of the first views of our planet hanging in space and saying, this is Spaceship Earth. We're all here together. We're all one
So
family.
the Charles and Ray Ames film was the inspiration for a little segment of an IMAX film that I helped to make called Cosmic Voyage.
Yes.
And rapid run through of the different scales that we showed, that 45-second video
Yes.
was taken from Cosmic Voyage. Anybody who wants it, you can, I think, find Cosmic Voyage at low res, not IMAX.
I'm going to stop screen sharing, okay?
Yeah.
There we go.
You can find Cosmic Voyage, I think, on YouTube. And anyway, I think the CD is still for sale. So it's an IMAX film.
I'm really impressed with that last aspect that we were talking about when Nancy was sharing with us the idea that we are moving from the individuality to the family to the community to
The web of life.
the web of life, getting more and more global in our vision. A little bit concerned that we're regressing a little bit back to tribalism recently in the political world and all of that. But there has to be that hope and vision that we move forward and that we can provide something that keeps humanity moving in that direction, as you pointed out.
And are the challenges of the day the instigation to revert back, right? Let's come into your resources, let's go to the tribe, that's a knee-jerk reaction. Or is it really the call to say, let's take that leap across the abyss and understand that we must come together. Like Bucky Fuller said, it's everyone or no one in humanity's final exam. I mean, we're at this critical crossroads. So which is it? Where do you find hope every day?
Everybody who's thinking about the future is saying, we need a new vision, we need a new vision. Where do you get a new vision? You can't make it up.
Right.
This is not the kind of thing that somebody's going to, some great novelist is going to say, here's the new vision, let's do it. A vision arises from a culture. it's not an individual creation, but it does have to have a foundation. And the way that you look for a new vision is you look, how did earlier cultures get theirs? And all, without exception, all the other cultures' visions were based on how they understood the universe to operate. And that was based on their observations, which, of course, since they had no telescopes or anything, their observations were simply eyesight observations. But what that ended up giving them was a picture of how they should live, how their morals should be set up, their vision for the future, their vision for their culture, based on a world that everybody agreed on. That's how it obviously was. The earth was obviously flat. There was obviously a dome holding up the water. Why was the sky blue? There was water up there. So what we need really is a foundation for the vision. We can't create the vision. I mean, obviously, Joel and I are not going to create the vision, but what we're doing is we're taking this modern picture of cosmology, which may very well be true, and to a great extent we know is true, but obviously more to be discovered. We're saying this could be the foundation, and we don't know of any other candidate. What other candidate is there for a vision that this whole world could share? We all share the origin story. We all come from the same place, not just us humans, all life on Earth. We all share this origin story. So if this could be made accessible, if it could be taught to children at a relatively simple level. Let me give you an example of this problem. So there's this cartoon that runs in the Sunday papers. And in the cartoon, this little kid asks, I forget, the mother or the grandmother or something, where does the sun go at night? And the adult answers, the sun goes to bed and God pulls a blanket over its head. That is the ancient Egyptian view. I mean, this is like what's going on teaching teaching a child a 3,000-year-old view when we know perfectly well what happens to the sun.
Right.
Nothing. We turn away from it. Nothing happens to the sun. Why don't they tell that to the child? This kind of crap really being poured into children's minds, and also being upheld by various religions, is just a disaster. And one of the reasons why we really need to move beyond the old-fashioned religious views of the cosmos.
There are some good tenets, though, in that ancient wisdom, that as above, so below, that the patterns of the universe that we see out there also make us up. We're not independent of it. Life is sacred. The web of life is sacred. We live in the community. The cosmos is a fertile womb of creation. Those are tenets that are worth pulling forward. So I would say that our early ancestors had some of that. They certainly had the awe and the wonder to behold the universe that leads us into a spiritual sense that there's something greater beyond ourselves. And
They
I think
do. They
that's
did,
worth
and
pulling.
we can draw that from this picture. So, like, just imagine, for example, remember the picture of the Ouroboros where all the sizes go around it. Okay. And we live in Midgard. What does it mean that the rest of the universe, we know it is there, but we can never contact it? We can't really ever come in touch with it directly. It is spiritual to us. In the ancient world, every culture believed that they were here at the center and they were immersed in a spiritual world. The Egyptians believed, for example, that the Nile ran from the spiritual world down onto their farms, and that they returned there after they died because it was there. In the Middle Ages, people also believed that they were immersed.
Had a relationship with the
Well,
cosmos.
if we look at ourselves on the cosmic Ouroboros, it's the same thing. Midgard is immersed in a spiritual world, but the spiritual world can be described by physics. And that is the fascinating thing here. Because all of the land of the gods and the land of the giants are real. But if we think of them that way, we start bringing in all the resonance and the power of earlier spiritual theories.
I agree with that we need to understand we're part of the whole and not a separate entity. And so, where does science and spirituality, Joel, come to you? You've spent some time also in those realms, bringing that together. How do you look at a universe and say, well, science has told us that it's a cold, dead machine slowly running down in entropy? How do you change that picture to say? How do you tell and speak to fellow scientists to say, no, this is alive and living, and we are part of its whole evolutionary arc?
So let me first comment on this thermodynamic idea that the universe is running down. Uh, so
That's also an old
Scientists-
idea we can overturn.
right. Well, no, it's just that that's based on a misunderstanding. So scientists and the general public often get very excited about recent discoveries, and thermodynamics was one of the great discoveries of the 19th century and the early 20th century. The grounding of thermodynamics in statistical mechanics and random motions. However, it misunderstands the way gravity works. So rather than running down, gravity actually does exactly the opposite. What happens as gas, for example, rotates around in the galaxy is that it loses energy because of collisions and things like that.
Okay.
The electrons in the molecules get excited. They then drop back down to lower energy levels, emitting radiation. The radiation is energy that's lost to the galaxy. In fact, it's how we see the galaxy. And the consequence of that is that material falls closer to the center where it gets hotter. It rotates faster. So the simple thermodynamic concept without gravity was that you take energy out of a system and it gets colder and it runs down. That's not how gravity works. You take energy out of a system, it gets hotter. And that process can go on for a very long time. So for example, the low mass stars that we see today, stars about a third the mass of the sun, they live trillions of years and they get steadily brighter. So our Milky Way galaxy will actually be brighter 1 trillion years from now. That's 1,000 billion years from now than it is today.
Wow.
And it could provide home for lots of living creatures on planets around such stars. So this idea that the universe is running down and on a time scale that's short is completely wrong.
Yay.
What is happening is that the universe is expanding faster and faster. We don't know how long that's going to go on because we don't really know what the dark energy is, but it could stop. But at the rate it's going, the distant galaxies are already disappearing. And even the nearby galaxies that aren't just part of our local group, which is held together by gravity, will disappear. The Virgo cluster will disappear in about 90 billion years at the current rate.
To our ability to see it. Okay.
Yeah, well, of course, the universe has only existed for 13 point something billion years. So we're talking about very long times in the future. And we also don't know, because we don't know what the dark energy is. There's a big effort to find out. It's one of the main things that the government is funding. And incidentally, that's because a very clever astronomer at the University of Chicago, Mike Turner, coined that phrase, dark energy. It's just a name. But because of that phrase, the Department of Energy has put billions of dollars into funding the search to figure out what the dark energy is. Very clever, Mr. Turner.
They like their black ops, I think. So
Okay.
we have to go with Bob. Bob actually worked on the Hubble.
Tony's first and then Bob.
And both of them worked on the James
Right.
Webb Space Telescope.
Right.
Yeah.
All right. Tony's first.
My connection with Hubble is that the biggest project in the history of the Hubble Space Telescope is the Candel survey, which is co-led by my Santa Cruz colleague, Sandy Faber. And I'm the chief theorist for the project. So I've had a lot to do with understanding what Hubble is telling us. And I'm also going to be getting the first images of galaxies from James Webb, currently scheduled starting about June 20th. So very soon. We've already made hundreds of thousands of images of what we think, according to our best simulations, these galaxies are going to look like. And I'll bet you we're going to be found to be wrong about at least some of the things we're predicting.
Tony and Bob gave us quite the talk along with their colleague Diana Dragomir, and Tony helped polish the mirrors for the James
He
Webb.
did more than just Paul. Anyway,
Yeah.
Tony, go ahead and speak.
Yeah. Well, first of all, I want to say how thrilled I am by this talk, Joel and Nancy. It's one of the best science talks I've ever heard, and it's absolutely lovely. Yeah, I led in your neck of the woods up in Richmond the team that polished all the Webb mirrors. So I had the privilege of doing that. And Bob, who will talk in a minute, designed the Webb telescope, did the optical design. So we have a little bit of connection here and great hopes of this, and are very
Well,
aligned.
thanks for all your efforts.
Well,
really
thanks for all you're going to do with it. I'm going to bring up a question that has bothered me. Several years ago at the American Astronomical Society, Bill Press had a special workshop on why do scientists not have public credibility, and he had some conclusions. But this is obviously seminal to the hope that you both express for our world. I wonder if you could talk about that and how we can change the perception of scientists.
I was recently president of Sigma Xi, the Scientific Research Honor Society. And what I was particularly pushing, not entirely successfully, was to get a lot wider range of scientists involved in communicating to the public. Most of the scientists, and certainly the ones that the public is most familiar with, are old white men like me. And that's fine for a certain fraction of the audience, I suppose. But the fact is that the most exciting work in science is usually done by the younger generation, graduate students, postdocs, early stage professors, and increasingly by women and minorities. And unfortunately, the public hardly ever hears from them. And what they do hear is often couched in rather technical language. So I think that's part of the problem, that we need to greatly expand the voices that are heard. The other problem is that the voices have to be much more effective. I heard Laura Lee, I think it was, mentioning that on Tuesday, there's going to be somebody who is particularly an expert in how to speak and how to use your voice. Our daughter is actually one of the world authorities on that. She's one of the top dialect coaches in Hollywood. So she's coached Gal Gadot in Red Notice, her recent movie, also in the second Wonder Woman movie, and many other famous actors. But she's also coached scientists. She worked with Alan Alda on teaching scientists how to tell stories. It turns out that that's the way you have to communicate. Most people don't like to learn lots of facts held together by theory. That's the way scientists like to think. Most people prefer to learn stories. We're built to generate and receive stories, and we have to learn to tell the ideas in a much better way, as well as using our voices much more effectively.
Very well
That's
said.
what I'd say on that. Nancy, do you have a
Yes, I
comment?
do have. So my comment on that is one of the reasons that scientists don't go out there and tell stories is not always because they can't, but because their colleagues will hold it against them. Because their colleagues will say, you are not a serious scientist. You have no business talking about anything spiritual or anything political. And this is really, I think, the biggest barrier, because scientists are really smart and they can learn how to tell a story, but they don't want to pay the price of not getting promoted or not getting published. So this is something that really the scientific community really has to look at carefully. Are we preventing the people who could save our planet from telling people how to do it in order to save the ability to publish their next
So
paper?
just for example, probably the best science communicator of the last generation was Carl Sagan. A lot of scientists resented Carl's popularity with the public. And he was, in fact, voted not qualified for the National Academy of Sciences, which was ridiculous. He's one of the great planetary scientists. He was the one who first realized that the atmosphere has to the greenhouse atmosphere in order to get around the so-called faint young sun paradox. The sun was only about 70% as luminous back when the Earth formed, when the solar system formed, as it is today. Carl also was among the first to measure the temperature of Venus and realized it was extremely hot. I mean, he made many important contributions, but people, other scientists held it against him that he was so popular.
Right. Right.
Well, may I also point it out, it's a lot of our tax dollars at work to support the sciences. Why aren't we, who are the supporters and stakeholders in the planet, why aren't we gifted with the knowledge and the story that it tells more readily?
We just recently
if I
had
could add-
Avi Loeb come on, and Avi was so passionate about the fact that I don't care anymore. This is research.
I'm tenured, I'm okay.
I'm tenured, I'm
And
okay,
I feel for those
and I'm going to challenge everybody. I'm going to ask questions.
So Avi, of course, is the former chairman of the astronomy department at Harvard.
Yes.
I know Avi well. I've known him since he was an undergraduate at Harvard University. So he's a very bright guy. He's done lots of important scientific work. And of course, his current hobby horse is that maybe not only was Oumuamua something that came from outside the solar system, that's almost certainly correct. But he thinks maybe it was some kind of artifact made
Right.
Now, there's been more recent work, I think, that he doesn't talk about that pretty much shows that that's very unlikely. But
I think that
anyway,
possibility
Avi's a
becomes the
smart guy,
question.
and I'm sure that the net result of his efforts will be that we'll expand our knowledge.
Okay, if I could continue, one of the findings that Bill Press had was the propensity of scientists to speak out with scientific authority about things they know very little about. and the credibility has been blown. I mean,
Nancy has a fantastic song about that.
Okay, I'd love to hear it.
It's on the web. It's called Hired Brain, and the full version.
It's a music video.
It's a music video.
I'd love to see it.
In her years working at Ford Foundation and the Office of Technology Assessment of the U.S. Congress, Nancy encountered lots of these scientists who could be bought, basically, and who were saying that acid rain doesn't cause any damage, cigarette smoking is fine for your health, and carbon dioxide is the greatest thing since buttered bread.
Well, how do we deal with that? I mean, I've always been careful not to speak about things that I can't go in depth. For example, I'm not an expert on solar evolution, so I'm not going to be talking about Earth-Sun
This is the
connection.
problem. This is part of the problem. You may not be a world expert, but you're a way bigger expert than anybody who doesn't know anything about it at all. And people, this is another problem with scientists. They're afraid to say anything in a field that they are not a world expert in. But if only world experts can speak, no one can pull the story together.
Yeah.
Who's going to tell the big story? No one is an expert in that, and no one can be. And that's what it means to have a story arise from a culture. People have to contribute what they have. For example, just lately, I forget the name of the guy, but one of the scientists who is a member of the IPCC, you know, who they write these climate change
panel on climate change,
said we should go on strike. I'm finished just writing reports explaining what's happening to the world when no one is doing anything about it. All of us scientists, we should go on strike. And you know what? They should. They really should. They should go on strike. They should march on Washington. Scientists should do these things because, you know, if you're just worrying that your reputation might be a little bit hurt by participating in the activism that could make your work valuable, then you're making a big mistake.
One of the problems that Bill pointed out was that, and he did a little test on the audience, and he said, how many of you believe that climate change is happening? And I think to a person, the hands went up. Then he said, I'm going to ask you another question, and the results will be different. How many of you think that GMO foods should be labeled as such? And it was 50-50. And there were people who were passionate on both sides of it.
Yeah.
So you have to figure, you know, if you have, there are topics like that which can introduce great entropy.
But this is a reason the scientists make fun of the public and then diss them, basically, because the public is not consistent. because nobody is really consistent. So the public accepts some science and doesn't accept other science because they don't understand what scientific method is. They don't understand scientific thinking. And some, like that cartoon, everybody going into the movie with the reassuring lie and skipping inconvenient truth. They may know, but they don't want to know because they don't know what to do about it, and it makes them depressed. So if you're just going to give people scientific information that scares them, they'll just close their eyes. They don't want to hear that. But if you give them scientific information that expands their sense of who they are as a human being, that gives them a community that they can start to feel part of, that's exciting, that can replace some of the bad ideas. You can't rip bad ideas out of a person's mind unless you give them a better replacement. You can't have a vacuum inside your mind. So this is the thing that we really need to do. We need to give people hope that they can change, that the world can change, that they can be part of a big, exciting, positive movement.
One of the things that Paul and Laura are doing that I think is absolutely magnificent in this program are having scientific points of view and intuitive points of view being represented not as at odds with each other, but that they can live together. And people who live in one way, they don't have to be able to solve a differential equation to understand what's at some level what's happening. And in fact, I would say the best discoveries I've made have come to me when I'm walking or dreaming, and then I go and do the homework and the math and the experiments. But it is interesting how things happen. Well, let me stop talking because I know that there are some great questions and comments. But thank you very much. I absolutely love this program today. It was magnificent.
Thank you.
Yeah,
Thank you,
indeed.
Tony.
Thank you.
I know that you probably have a timeline. It's Mother's Day. We do have 3 or 4 more questions. Can we do those questions?
Oh, we have to hear from Bob.
Yeah. Okay. Bob is next.
Thank you,
Yeah,
Tony.
hi. I really love the talk today. It's really great. Yeah, I did the design of advanced camera for surveys, but with Holland Ford, we talked a lot about the deep fields. I designed the Kepler. I did the initial design on JWST. I know John Mather very well. I have an observation. Each of the cosmologies you described, including the 4th one, puts man at the center. And I cannot believe that we can come together as a culture unless something bigger than that is at the center. Say the saving of the world, and each of those cosmologies put they brought together mindsets, but they were only local mindsets. The religions still fought against each other. They did not have a global expanse. So I don't know how we get a global expanse. We've had COVID, which should bring us together as a world. We have global warming, which should bring us together as a world. These are global threats to us, and invasions by a foreign, it's like the day the earth stood still in the movie of the 1950s. I thought something like that could bring us together as a world, but I haven't seen it. So that's my observation, and I'd like to get your take on that. So.
Well, I think we did talk about that. I mean, the idea of bringing the world together, people come together when they realize the stakes. So look at Ukraine, for example. Ukraine was actually quite divided politically, and there was Zelensky was not really all that popular until the invasion. And then suddenly Ukraine comes together and everybody is fighting because they know they're under threat. So this is really the same situation with the Earth. Yeah. We are at each other's throats, largely because we have these different religions that have different value systems and different divisions of who's us and who's them and so forth. We are facing a threat, but we don't recognize it. And this is really what we need right now. We need people to understand that the threat is to the entire planet. By putting us at the center of this new cosmology. What we're saying is that we are not for anthropomorphic reasons, but if you look, for example, at the fact that we're at the center of all possible sizes, this is a physics phenomenon. Physics is the same all over the universe. It's not going to be different for aliens. It's not different for anybody. We're at the center of all possible size scales because we're at the peak of complexity. That's where intelligent beings have to be. So it's real that we're central. It's real also that we're at the center of the cosmic spheres of time, not because we're special, because every galaxy is at the center of its cosmic spheres of time. The point is not that we are right and other people are wrong. The point is there is a really interesting, meaningful way that we can now start to see a big picture that is shareable. It's not shared yet. People don't know about it, but it's shareable by everybody on this planet. And this is the first time we've had a foundation for that kind of a picture. It's not going to happen instantly, but yes, if scientists will get out there and everybody else will get out there and start talking about how this applies to all of us, it could really help.
Well, I guess I
Our
don't
bandwidth and
understand.
expand our boundaries.
I guess I don't understand how it become global as opposed to local, because as you know, over the last several thousand years, well, in the 1918, you know, there have been several things that could be that could bring us together globally, but none of them have, and COVID did not. So, and
Yeah,
I
but
don't
you're
know
talking
how-
about disasters. Disasters aren't going to bring us together. Something positive is what it takes to bring us together. We have to want to be there. My favorite quote, or at least one of my favorite quotes, is, "If I can't dance, I don't want to be part of your revolution." Okay, that's Emma Goldman. If I can't dance, I don't want to be part of your revolution. If I'm going to be miserable, what's the fun of joining this movement? A movement should be there to lift us up. If you like, what I can do is read you the shareable principles of a planetary morality that's in my last book. And this is the kind of basis that I'm talking about. Principles. We can have a shared picture on a big scale while maintaining all of our diversity on the scales that, you know, we notice every day while we're alive, but we could still share the big picture. I'm just going to read, there are 8 principles here. I'm just going to read them to you.
I want to hear him. Yeah.
1, Earth is extraordinarily special in the evolving double dark universe, and beings like us may be rare or even unique in the cosmos and must be protected. 2, truth is the only foundation for a shareable, coherent picture of reality. 3, it took almost the entire age of the universe, 13 billion years, for us to evolve, and our descendants could live comfortably on Earth for another billion years. The 21st century is the pivotal moment when human decisions will make this future possible or impossible. 4, for a sustainable future, our current exponential rate of resource use must end and become slow material growth supported by boundless creativity. We must do more with less. 5, emergent phenomena are inevitable as any situation becomes substantially larger or more complex. So anticipate them, accept them, work with them, and be humble before reality. 6, there is one magnificent cosmic origin story, and it is equally true for everyone on Earth. To know who we are, we must tell it in every language, every medium, and every generation. 7, we humans may be the beginning of a multi-billion-year blossoming of intelligence in the visible universe. So let's act as if we are. Let's think of ourselves as the hottest startup ever. 8, God emerges from our aspirations. So embrace aspirations worthy of the kind of God you want. None of these principles conflict with anybody's religion.
Yeah. And it's not only a new story for who we are, but it's a call to act. It's a new identity about who we are.
New identity, exactly.
Yeah. And the responsibilities, the covenant that we have with this greater emergent evolutionary arc that we're involved in.
Thank you.
We need
Thank
to emerge to that next phase. We
We
need
need
have
to
the
make it
knowledge,
fun. We need
we
to
have the
make it exciting.
technology, we have the opportunity, we have we have everything here.
We have to maintain optimism. Also,
Yeah.
we have to just feel like there
Well,
is
this
an
is-
but yeah.
But to behold with awe and
Yeah.
wonder the immensity of the universe and our
Right.
place in it, that's it puts you right in that spiritual
Right.
stance already.
Yeah.
Yeah.
Yeah. Yeah.
Yeah. Thank
Well,
you both for the
yeah.
beautiful work.
And
you
Bob,
do.
that was a good question. Thank you
Yeah,
for,
and insistent.
pressing on that.
Brian, we must hear from you.
I got
Yeah.
2 more hands up too as well. Go ahead, Brian.
I just want to say, beautiful talk. I'm so thrilled to hear these views articulated. And I hear spirituality woven throughout what you're presenting. And I wondered if you could speak a little bit more. You have already spoken about emergence. Nancy, that last quote, basically that the God emerges from our aspirations. I wonder if you could say a little bit more about the role of this theory of emergence and how it might help integrate spirituality and science from your view.
Yeah.
This is the foundation. This is the basis of my book. So I have been in a 12-step program for 34 years. And when I first got in, I was quite an atheist, and I could not imagine how I could do this, because this is a 12-step program. Is basically you have to sort of refer to a higher power to help you do something you have not been able to do before. So
Right.
I did not have a lot of hope for myself in this, because there was no way I was going to believe in a higher power. So, but I had no choice. I had to find some way to think about it that was meaningful to me. And seriously, it took me about 20 years in this program to figure out how I could think about it. And I realized that if a higher power, or God, which I am using the word God, if a higher power is going to be useful to me in my life, it has to be real. If it's not real, there's nothing there. It's not going to be useful to me. So I thought, how can it be real? And I thought the only way it can be real is if we start from reality and we ask, is there anything in this new double dark universe which actually contains many possibilities no one has thought of yet?
Yeah.
Is there anything that could plausibly exist that is so godlike to us that we might as well call it God? Because that's God. That's it. If it's godlike to us and it absolutely exists, to me, that's God. Okay. So what occurred to me was that the only thing that could be that to us would be something more complex than we are. And where could it come from? It could only emerge from humanity. Now, emergence is such an interesting idea, because it doesn't mean that humans created God. It means that through the laws of nature, through the laws of complexity, when many, many, many humans interact in a certain way, something new emerges. So we know, for example, the economy has emerged from us. Governments have emerged. Science has emerged from it. All the major collective endeavors are real, but they're not solid. They're not human. There's something new. There's something astonishing that have arisen. So what would God have arisen from us doing? Well, it has to be something that we've been doing since before the gods emerged, right? So what could that be? And I realized it is aspiration. We are the aspiring species. When you look at other species, they do change in order to adapt to environmental circumstances, or occasionally, some creature will learn how to wash a potato, and then the other ones will wash a potato. But very, very small changes. But what about us? We aspire from, interestingly, about the age of 18 months. That's when children really start to aspire and pretend the world is different. There's actually a wonderful book about this called by Alison Gopnik, where she actually did research. So from the age of 18 months until the minute we are dead, we are aspiring. Even on your deathbed, you either want to die or you want to live. So aspirations, everyone has different aspirations, but we are aspiring all the time. And that is what guides us. That is what gives us the direction of our lives and gives us our sense of values. So everybody's aspirations are interacting, right? And out of that interaction arises a reality, an emergent phenomenon. And I think this emergent phenomenon is real. Whether you want to call it God or not is a matter of taste, okay? But the emergent phenomenon from all of our aspirations is something that has given us language, cooking, things that we can't live without. Everything that we have done collectively has arisen because our aspirations have interacted. So that to me is a reality. And as you know, the emergent phenomenon and the lower level participants, shall we say, that create it, it's a two-way street. They affect each other. And so the economy affects all of our decisions about money, right? When you can invest this, what the economy is doing affects us, but there would be no economy without us doing those things. So it is absolutely a two-way street. And I see God that way too. I see God as a something that is changing instant by instant in billions of ways because of all these people putting in different aspirations, but we feed it. And if we feed it good aspirations, we will have a better God.
I would love to invite you back to another Sunday, Nancy, and really go into depth in this in your book, because that is so key to how we shape the values and our goals and what we're going to collectively do together.
Yeah.
I mean, so often we think of wealth and having enough as God must be rewarding me for good action, right? That very old idea. But the ancient idea of living in right action and beauty and grace is a community that functions, being in right relation with oneself, being in right relation with community, being in right relation with the cosmos. I think that's where we need to be, not just that I'm rewarded for God bestowing his gifts on me, but that our community, our world is rewarded for right action. And we need to shift to say beauty is a peaceable kingdom. Beauty is the world at peace with everybody having enough and the species all living together and the web of life in harmony. I mean, if we can shift into that idea, we can start to build that as the goal. I think that you're getting to some very underlying ideas that are so fundamental. Would you come back sometime and
I would be happy to, because I see this as one more angle on the big picture.
Yes.
You cannot have a big picture without God. It
Yes.
isn't going to happen.
Yeah.
And but what God is completely open to interpretation. And I think we really need to think about that a lot more deeply than people have been doing.
We need to make this shift.
It's
And I
essence.
agree, we can't just throw everything out and start over. We need to build, because it is the arc. We need to build from the past, but know the past, understand ourselves, and then build a future that makes sense, that we can all agree on. Diversity and the unity. I mean, it's key. It's our job today, isn't it not? Mm-hmm. Yeah. And we don't have to accept the worldview that our society gives us. It's up to each of us, and that's why I think it's so important to find our authentic self and our authentic voice, because each of us need to add to this picture and build it. Well, I don't have to be a scientist with your credentials to have a voice and say, this matters. I have a view here too to share. I speak for the ancestors in our work.
Thank you both for your voice. I see there's
Brian.
still another question here, so I'll sign off. Okay, thank you.
Thank you, Brian.
This is so pivotal.
And Shoshana's up next, and exactly. I know that I was noticing Stephen Seiden made a couple of great comments about Buckminster Fuller and how he was saw as a
Stephen's been a
kook or
guest.
something and pushed to the edges. Coming back to Tony's topic, but so thank you for those comments in the chat room. Hi, Shoshana.
Hi.
Yes.
I know there's not much time left, so I'm going to try to be really fast. But I'm an artist, and I know a lot of scientists. I'm very interested in science. I belong to a group called the Sci-Art Initiative that brings artists and scientists together. I've worked on museum exhibits on science and done a lot of the displays, illustrations. So this topic of the scientists trying to communicate and emotionally move a person, or touch their, what you could call their heart, touch their caring, is something I feel the scientists could work with more artists. I don't, you're right about the way the language of the scientists is often too technical. Nobody can understand it. And then it's dry. A bunch of graphs is not going to inspire somebody to, emotionally. And I think that unfortunately, a lot of scientists do not know much about the humanities, and they look down on it. And of course, it goes vice. The people in the humanities don't understand the scientists. So I think this need for collaboration is urgent. I mean, that's me. That's my life. And I wanted to show one painting that I did. I was a follower of Lynn Margulis. I read a lot of her books. And when she died, I was working and I heard that she had died. And I was so sad, even though I didn't know her personally, but her work had just changed my whole way of looking at life. And her book, What is Life? Her and her son, Dorian Sagan, Carl Sagan's son. So I did a painting, and I'm going to put it on the screen. I think I can get it there. There it is. Okay, so I'm going to get it away. Okay, this painting is based on her work, and it's based on illustrations from her work.
It is wonderful.
Well, that's what people now. Okay, so everybody loves this painting. It doesn't matter whether they're a scientist or not. And after, when I was at her memorial, I presented this painting, and I met some of her colleagues, and one of them wanted me to do some illustrations for his book on I think he's a geologist, geophysicist. No, he was a geologist. So, but then he told me I can't put it on my book because it's not scientific. And my book is a scientific book, and it will not get the credibility that it needs. Mm-hmm. So we need this ability to look at a painting like this and understand this is a metaphor. This is a piece of art. It's not a scientific illustration. But we have to make room for this, because this is what gets people saying, "Wow, I love this. This is inspiring." And my goal, in a way, as an artist, is to help people see how beautiful the earth is, and just paint beautiful paintings about nature, and in a different way. A lot of my work is based on microscope images, and that blue dragon, that blue snake is based on a microscope image of phospholipid tubules that David Deemer from your university at UC Santa Cruz provided in Lynn's book. And I've made contact with David, and we have an exchange going, and I'm trying to
David and Nancy and I are great friends.
I'm trying to do a painting on, what do you call it, on protocells. I'm trying to get UC Santa Cruz to buy this painting, this original painting, because that's where David is. That's where Donna Haraway is. That's where you are. So if you have any influence, David,
I want to say, I want to look at your Sci-Art initiative. Paul and I have been invited by a museum to do an exhibit on the power of ancient art.
Right.
And I will say that the ancients were very good at metaphor, very good at symbology and iconography. There's a lot packed in there of wisdom, and I think science and the arts need to embrace one another. That's certainly why we cover the arts to the sciences.
Shoshana, wonderful. Yeah.
Thank you. Thank you for Please drop us a line.
Yeah, stay in touch with us. We want to talk more. Absolutely.
Good. Okay. I'm going to mute myself and all of that.
Every cosmology in the history of the world has been communicated through art.
Yes.
Yes.
Tell more scientists that.
And ours will have to be. It will have to be. Otherwise, no one will get it. And I'm an artist too. I'm a songwriter, and I have many songs that try to bring out the meaning of science. I'm very often, in fact, the entertainment at scientific conferences.
Well, we'll have to hear some of that.
You're very
and I did watch your film.
Play some of them.
When you come back. We'll cover that. Yeah.
So a quick way to get links to all of this stuff is nancyellenabrams.com. Just name all spelled out, no spaces. nancyellenabrams.com. That is linked.
Thank you. I want to hear from Lloyd. From Stephen Seiden. Rather, he's a Buckminster Fuller biographer. And
I don't know.
You mentioned that we have to use our resources wisely because we do have enough if they're used wisely, which was
Okay.
Bucky giving us solutions for tomorrow, today, which we need today. Still haven't listened.
Yeah.
Is he still here?
Well, he is here, but
Yeah.
you caught him off guard probably because he didn't have his hand up.
Okay,
There he is. He's coming on. Hello,
so much
Stephen.
to add to this, Stephen.
Yeah.
Well, everything that's been said fits directly into everything that Bucky taught for 56 years, from the time he had his awakening till the time he died. And the solution is really simple. And the Earth will, Bucky used to talk about this all the time. The Earth will be fine with or without us, but we're a species on the verge of extinction. And it could happen tomorrow, could happen in an hour, could happen in a year, but we're there. And what reason is, and then Bucky talked about this all the time. If we don't shift from weaponry to livingness, shift our resources and focus from weaponry to livingness, we're basically toast. And this Ukraine thing is like, yeah, Biden will sign billions of dollars of money to send to Ukraine, but I live in Seattle and there are people sleeping in tents, and people can't pay their college debts. This is all living, and
had we done it in the 1970s, Nancy, as you pointed out, when the scientists first knew, if we had the will to take the steps, we wouldn't be in the geopolitical bind that we are today. Right.
Yeah.
Well, anyhow,
or the environmental bind that we are today.
I just put a couple of comments in there. I didn't really want to speak.
Oh, you did great,
Well, thank
Stephen.
you.
Thank you for
Anyway.
adding it. And yeah, it's the visionaries along the way who bring up these ideas maybe don't get recognized till after they're dead, whatever.
Bucky was labeled a crackpot by most people during his
Yeah.
life. I mean, they thought he was crazy because he thought that we could actually survive and thrive as a species.
Yeah.
And that nobody had to die of starvation. The 50,000 people who will die of starvation, who don't get on the front page, by the way, but every day, that didn't have to happen.
Right. Thank you, Stephen. And
You're welcome.
thank you all for joining us today. I mean, this has been an amazing and fantastic discussion. What a powerful couple we just met. The way that they share information and knowledge and their keen insight, their research. To me, this was one of the most fabulous discussions we've had. It's just been building and building and building, and what wonderful knowledge and information you bring to the table. And on this day of Mother's Day, which probably is a good day to think of God as a female.
Thank you, Pat.
Yeah, Mother God or something. Yeah, today's the feminine, and
To really celebrate Mother's Day is to celebrate our planet Earth and the call to action and our duty towards our special place in the universe. Thank you for bringing it out in the ways that you do. I mean, you make such a solid and strong case, and I particularly celebrate a husband-wife team that works together and that strengthens the message from the both halves of that equation. So beautifully articulate what careers that you've had, and that you're bringing it to all of us, that you're bringing it to the general public with such an important message, making it a story that we can understand, making it inspirational, giving it voice, speaking on behalf of that universe and these emergent evolutionary principles, because we are given what it will take, right? I don't really understand what's holding us back.
Could I make one response to that last comment? We on Earth, we human beings may be the first of our kind. We could be the seed of intelligence in the entire galaxy. And Earth may need to put up with us. We may be bigger than the future of Earth, the planet alone. But if we're intelligent, we'll understand this and realize that we are completely physically dependent on this planet. So I feel like just saying the earth is toast, or humanity is toast, and the earth could do fine without us. The earth could do fine without us, but the galaxy might not. The galaxy might never have intelligence. It might never develop the way that it could if we can keep ourselves going long enough. So, take the bigger view. We could be the hottest startup ever in the history of the galaxy.
I like that.
That's a beautiful
I was also wondering, it's time to also revisit the stories that we share. So every story that you see of alien civilizations coming into Earth, rarely are they beneficent aliens. But if they got here, they would know what you are trying to say is that intelligent life in the cosmos is very rare, very precious. And that I'm thinking there are going to be more stories where they come and help us out, right? To see this big picture that they're like, okay, you need a little tinkering here, humanity, to really be in your full potential. We've made it. Let us show you how to leap across this abyss that you're facing. I'd like more stories than that. I'd like at least Star Trek and was about let's be a good force out there as we go exploring, right? We can explore from an armchair, right, safely here on Earth. And I want to also tell Elon and Jeff, it's not as simple to go out and terraform any old planet. Just like you pointed out, it needs the planet itself cooperating to maintain that atmosphere, to maintain life. To be in that special sweet spot in the universe. It's not as easy as just taking all your tech and wealth and going out there. It needs to be a collective global effort, and we need to get it straight here. We need to write our own path, our own house. We need to get it going here first. Can you concentrate, please, on this? Plenty of time to go colonize other planets. We need to get it together here first, please. And there's many other things that you could do with your wealth to help facilitate this. Just want to leave that message out there. This is not an escape for all the elite to go out there and think that leave the hoi polloi behind, right? So your final words on this, and thank you for spending a little extra time with us. Tell your daughter hello, and we'd love to invite her back to our Sundays as well.
Oh, yeah.
We'd like to invite you both.
Especially with her.
You got more to share, more stories to tell. And defining God, isn't that one of the ever eternal sticking points for humanity? How do we define a creator?
Well, I don't define it. I just have an origin story for it.
Thank you, an origin story for it. And final thoughts, and let us thank you.
Since you were kind enough to follow up on what I mentioned about our daughter, so she has a major book, a huge advance, coming out February of next year, February 2023. The name she uses, her stage name, as a member of the various Actors Equity and Hollywood unions, is Samara Bay. Her real first name is Samara, Samara. The name she's using is Samara Bay. That's her stage name. Samara Bay, all one word. And if you go to samarabay.com or ladialectcoach.com, you get links to all of her stuff. So she's had many, many interviews, including on CBS Sunday Morning. New York Times Magazine featured her. And so links to all of that. And she's got an amazing podcast. Anyway, all of that is linked to samarabay.com. And
perfect.
Try inviting her. She may be able to fit you in.
Sounds like she's a busy gal.
Wow.
Thank you. Fabulous. Well, again, thank you both so much for being here. And what we usually do is we end our program is we ask everybody to say thank you as well. So we say, turn on your mics. Obviously, we've gone over time, but everybody want to say goodbye and thank you to the guests.
Thanks.
Thank you. Thank you, Joel, Nancy.
Many thanks.
Many thanks.
Thank you. Thank you. She McWitch.
All right.
Well,
Beautiful.
Thanks, Paul and Laura, for inviting us.
Blessings to everybody. Good health.
Thank you.